I'll just also introduce myself. I'm Auke IJsbeert. I'll be a bit the host here. And so, hello, Michigan. We're very happy that we can join you by video conference. And there's a big room here, so we are not just the two of us standing here. So I like everybody to make a big shout for Hamed here. So yeah, the happy people here, and we're very happy to be part of this. So maybe let's go with the talk, and then we give you the certificate. I have it here, but I just want to make sure you give a good talk first. So let's start with you, and hopefully everything will be fine technologically.
Okay. Before I start, I want to say that it is a great honor to receive this award today. But this wouldn't have been possible without my PhD advisors, Professor Jesse Grizzle and Professor Tony Block. So I had the privilege of having you two as my PhD advisors. I learned a lot from you, and you did a lot for me. And I would like to say thank you so much for all that. Also, I would like to thank the math department and specifically Professor Peter Scott and also Auke IJsbeert, my supervisor here, for arranging all this, and also the video conference team here and the University of Michigan. It's unfortunate that I cannot be there in person, but I'm happy that still I'm able, thanks to technology, to present to you my PhD research, which is on symmetric hybrid systems, periodic gate design for legged robots. So yeah, so before even talking about symmetry and periodic orbits, I want to say a few words about legged robots and why legs at all. Why should we care about legs? So that's the first question that I want to ask. So why, for example, not wheels? We know that wheels are very energy efficient as long as you have a continuous path of travel, even ground, right? But what if there's a discontinuity in the path of travel? Okay, do you still go by wheels? I don't think so, right? So instead, what you do, you use legs, right? So legs can go places that wheels cannot go, right? They can go upstairs, ladders, rough terrain, mountains, right? So this versatility of legged robots, however, brings some challenges, okay? One of the challenges is energy efficiency, and the other one is stability, right? So the wheeled vehicles, we know that they're already very energy efficient, right? So if you want to build a legged robot, you have to be very energy efficient. Otherwise, you cannot even compete with wheeled robots. And I mean, if you can do okay in energy efficiency, then you can say, I can do more, because I can go to trains that you cannot go, the wheeled vehicle. And the other challenge, I really didn't research much on energy efficiency in my PhD. Mostly I was concerned with the second challenge, which is stability, right? So legged robots, they have many degrees of freedom. They have this impact map, as you walk, your swing foot hits the ground. We have this impact nature and a small support area. All of them makes the stability a challenge, right? So there have been different answers to this question of the stability and how to design a stable walking gait, right? So the very first ideas that came, many years ago was the idea of a static walking. In static walking, what you require is that you say, I have this robot. If the projection of the center of mass is in the support area built by the legs or the feet, then I'm stable. This criterion, however, only holds true if your robot walks slowly. This is like the stability of this table here. So this is a table, and this is the center of mass, and this is the support area built by the four legs, right? So this criterion is really saying that if the projection of the center of mass is in the support area, then you are stable. Now imagine that this table is walking slowly, right? And with three legs on the ground. Still, this criteria could hold true if the the robot walks slowly. This is an example of a static walking. This is ODEX1 from 1986. I don't know how is the quality of the video in Michigan now, but yeah, this is a six-legged robot walking, and it's, as you see, it's very slow. So it's like if you turn off the kinetic energy of the robot, you make it zero, the robot doesn't fall. You know, at the same, it's that slow. You know, that's what I'm going to say. So another criterion known as ZMP walking is, or zero moment point walking, says that, you know, I don't require the projection of the center of mass to always lie on the support area, but I require the resultant of all the ground reaction forces to lie inside the support area. Although this one allows non-static walking gaits, right? It does not allow, I mean, all the range of walking gaits that you as a human can get, for example, or animals out there. So there are many dynamic gaits out there, and every day that you walk, you know, you don't walk ZMP stable or in a ZMP way. So even though it's less restrictive, still it is very restrictive. So it doesn't allow you agile and dynamic legged locomotion. And the last one, which is my favorite, right, is dynamic walking. In dynamic walking, you require only a stable average behavior. Compared to the static walking. In static walking, we said that, you know, we require the projection of the center of mass to always lie on the support area. Dynamic walking says that, you know, I don't require that. All I care is that you are in average good, or in average, the projection of the center of mass is on the support area. So you move around, you walk, you fall, catch yourself, but on average, you're in a good shape. Okay, so that's the least restrictive one. Okay, and that's why you can allow a number of interesting gaits. This is the bipedal robot or humanoid robot Coman at the Biorobotics Laboratory here at EPFL. So this is built by Italian Institute of Technology, and I had the chance of to work with this robot in the last 6 months. And I tested this symmetry method on this robot, which has 23 degrees of freedom. And here is a video of this robot stepping in place to show you this idea of dynamic legged locomotion. As I said, you move around, but on average, you're in a good shape. So look at this video. So as you see this robot, you know, this is going to the left leg, right leg, and if you look carefully, you see that it goes to the edges, you know, in the leg, in the foot. So, and I even push it, but on average, again, you have this stable behavior. So there is one thing wrong, actually, not wrong, difficult with this idea of a stable average behavior. It is simply too general. It's not easy to find a control algorithm that can realize this criteria. What does it mean? Even though it's not difficult to formulate that mathematically, finding a control algorithm that can realize that is not easy. So what we do is that I think the next best, which is limit cycle walking, right? In limit cycle walking, you model the legged locomotion, or you search for periodic gaits, you know. And if you have a bunch of periodic gaits all together, you can achieve a variety of gaits still, okay? And also every day as we walk, you know, walk around, a lot of gaits that we have are actually periodic. So finally, I think it's a very good start, you know, if you want to get to the general dynamic behavior. I think if you solve this problem first, then you can think about non-periodic gaits as well. So now this is actually the focus of my PhD. If I give you a legged robot, okay, how do you find a periodic gait that is stable for that legged robot, right? So if I ask you this question, maybe the first idea that comes to your mind is that, okay, I have a legged robot, right? You see here? So what I do is that I model this, right? I model this robot, and then what I do, you're looking for periodic gaits. Periodic gaits are periodic solutions in the dynamical system, okay? So what you do, you search for fixed points of the Poincare map in the dynamic system. And then those fixed points of the Poincare map, which are the periodic orbits of the dynamical system, are the periodic gaits here. That's the natural idea and very, very common, actually. However, there are a few points here that I have to make that makes this method not actually the best method. So what are the problems? This method of searching for fixed points is computationally expensive. Why? Because when I say you're searching for fixed points, it's not just a simple search. You have to integrate all the equations of motion and check if the equations of motion go back, if the initial point goes back to itself, right? So you find the solution and check that. And these systems have many degrees of freedom, so it's computationally expensive. They do have this robustness issue, which means that, your search is based on a model. So what if something in the model changes? Is the fixed point still a fixed point? If it is a stable, is it still stable? So we have this problem of robustness issue there as well. Finally, because you check, the fixed point and then the Jacobian, the eigenvalues, it only guarantees local stability. And actually, at the end, I believe that, if you want to work with legged robots, one single periodic orbit is not the solution. You need a family of periodic orbits that are working together, So the symmetry method that I'm going to explain today to you, to some extent, as long as the time allows, solves some of these problems. Why? The main reason that it's solving this problem is that it doesn't require searching for periodic orbits, right? It says, okay, you don't need to search. All you have to do is that to detect the symmetries that exist in legged robots, and all of them more or less have that, and then just respect those symmetries. So the controller has to respect those symmetries. Then the result is that you get an infinite number of periodic orbits without requiring to do search. And that automatically gives you the robustness as well, right? So you have a family of periodic gates. In the previous video, I showed you the video of the Coleman walking in place, right? That was one single member of this family using the symmetry method. By changing one single parameter, for example, the step length, I get to this walking gate here. This is the walking gate that we got like a couple of months ago. It was, as I mentioned to you, just the stepping in place, change one single parameter there, and then you get to another member of the family. So now it's walking forward, right? So this is all based on the symmetry method. So in the next few slides, I try to explain how does the math works, to get you into this periodic gate or stable periodic gates or the family of limit cycles. So I first talk about symmetric vector fields, then symmetric hybrid system. Then I explain why legged robots are symmetric hybrid system, which means that they have an infinite number of periodic orbits. Finally, a few slides on the stability of symmetric periodic orbits, and finally, and at the end, experimental results of this symmetric method. It's more videos of Coleman, indeed. Okay, walking. So now let's start some math. Okay. So symmetric vector field. What is a symmetric vector field? So imagine that you have a manifold M. Okay. When I say manifold, if you're not familiar with that, just think of Rn, R2, right? Just a normal space, real space, two-dimensional, three-dimensional. And we have a vector field X over that. There is a map G from M to M, from Rn to Rn, if you wish, right? So here is the definition of a symmetric vector field. You have this vector field, which, it has the equation, the dynamical system corresponding to that, the symmetry map. If this equation, just pay attention to this equation, holds true, then I say that X is a symmetric vector field. What does that mean? That means that X OG is equal to minus dg, which is the Jacobian of G times X. That is, if I calculate X at a point G of P, for example, it is like calculating X at point P and then transferring it by negative dg, Jacobian of G, to the point GP, so that the result would be the same. Let me show you this figure here. Maybe that helps giving you some intuition of what I mean by a symmetric vector field. So this is just R2, so I'm assuming that my manifold is R2. So I have a vector field that is symmetric. This is a vector here. As you see, this is one of the vectors at point P, for example. And this is the vector field at point G of P. And this is an integral curve of this vector field. Okay. So and the symmetry map is sending x1 to negative x1 and keeping x2 the same. This is the symmetry map. So what is happening is that x at point P, if I multiply dg, the Jacobian, I transfer it to point GP, I get this green vector here, right? In a symmetric vector field, if you multiply this by negative sign, you get x of g of p. As you see, x of g of p is minus dgpx. Okay. So why this is interesting is this solution here. As you see, this solution, which is passing through the points 0 and 0.5, okay? If you plug in points 0 and 0.5 into the symmetry map, what do you get? 0 for x1, 0.5 here, I get the same point, 0 and 0.5. So this is called the fixed point of this symmetry map. Any solution that is passing through a fixed point is called a symmetric solution, which means that it satisfies this equation. That's why this might be interesting, right? Otherwise, you know, yeah, who cares about like a symmetry map and everything? They do have these symmetric solutions that later I talk why they become interesting, okay? For now, for those who are roboticists, that might be a little boring, but we get to that with the application of this to legged robots as well. So in any case, what is this saying? It says that if you have a symmetric vector field, any solution of that vector field that is passing through the fixed point of the symmetry map satisfies this equation, which is that if you apply g on x of t, you can go back in time to time negative t. Another way of saying that is that if you have half of the curve, we can figure out the next half. From time negative t to 0, you can figure out what is from the curve from time 0 to t. This is an example, a simple example of a symmetric vector field. You can verify that this is a symmetry map for this vector field. And that equation here, based on this symmetry map, simply says that you have odd and even solutions. So by just looking at this vector field and the symmetry map and the fixed point of the symmetry map, you can figure out that there are infinitely many solutions for this equation, which are odd in x1 and even in x2. Okay. So as many as the fixed point of the Poincare of the symmetry map, you have symmetric solution in a symmetric vector field. 1, 2, 3, as many as those. Okay. So now let's get to some legged robots example. How is that related to legged robots? This is perhaps the simplest legged robot that we can imagine. This is just the inverted pendulum moving from this point, negative x0, to point x0. If you write down the equation of motion, x double dot equals omega squared x. If you write this in the status space form and the vector field, you will easily see that this is a symmetry map. So it looks like that some of the legged robots are actually described by symmetric vector field. You might say that was too simple. How about this one? 2 degrees of freedom. It is a double inverted pendulum. You can think of it as your stance leg plus the upper body, right? So it turns out that the kinetic and potential energies of this system are invariant under this map, which is a symmetry map. That is changing theta 1 to negative theta 1, theta 2 to negative theta 2 does not change the kinetic energy and potential energy of the system, and keeping theta dot 1 and theta dot 2 unchanged. Kinetic and potential energy give you the Lagrangian, right? So that means the Lagrangian is invariant under this map. And so from that, we can show that the vector field that is describing this dynamic system is a symmetric vector, okay? If you don't like that explanation, just look at these two equations. What does it say? In other words, is that theta dot 1 and theta dot 2, double dot 2, if you write it, f and g are odd functions with respect to theta 1 and theta 2, okay? How about another more complex like that? Look at this one, 5 degrees of freedom, x, z, the swing leg, and the pitch angle. Again, look at the kinetic and potential energy. They are invariant under this map. What does that mean? They do have, this robot does have an infinite number of symmetric solutions. And based on this symmetry map, these symmetric solutions are just odd even solutions here. Okay. So you might say, okay, why should I care about odd even solutions in a legged robot? Why should I care about that? why these are interesting at all? The answer is they are not. They're not interesting. Unless you add hybridness to it. So once you add hybridness to these systems, which are actually the models of legged robots, by the way, these solutions become interesting. So quickly, what's a hybrid system? So in a hybrid system, you have a discontinuous phase, which is like your vector field. But you do have a discrete map as well. Because as you walk, your swing leg hits the ground, and the roles of the swing leg and the stance leg switch. So you can model the walking as a hybrid system, okay? So the solution starts from some point, it hits the switching surface, which in walking is defined by the height of the swing leg, and then it is mapped to a new point based on the impact map, and then you continue the solution. So now, the definition of a symmetric hybrid system, okay? So I gave you the definition of symmetric vector field, now symmetric hybrid system, which means that I add the hybridness to the definition, of course. So you have this x dot equals x and the impact map, or the discrete map. So of course, you expect this, as I've explained before, x is a symmetric vector field, but there is another condition on the discrete map, and that is this condition. It is saying that, sorry, because I cannot use the pointer, because in Michigan you cannot see the pointer, so I have to use the mouse here. So the discrete map condition is that the discrete map or the impact map on a symmetric solution is the same as the symmetry map. So we have a symmetric vector field here, and another condition. Your impact map is the same as your symmetry map on a symmetric solution. With these two conditions, you have a symmetric hybrid system. And why is that important? Look at this symmetric solution that we had before, and it was not interesting to you, right? Just symmetric. But now I know that the impact map is the same as my symmetry map. So the symmetry map is sending this point to this point to this point. So now with impact map, I have a symmetric periodic orbit, right? So all those symmetric solutions in a symmetric hybrid system, they become symmetric periodic orbits. So the point here is that if I show to you that legged robots are symmetric hybrid systems, then I can say that they do have these symmetric periodic orbits. So you don't have to search for them. So only your controller have to not to destroy that symmetry. That's the only job of the controller that you design. So again, a symmetric solution of a symmetric hybrid system, that's the main result really here, that of a symmetric hybrid system is periodic, okay? Let's give an example of a simple 3D biped robot. It is called the linear inverted pendulum, which is the height of the center of mass is constant here, as you see. If you write down the equations of motion, x double dot equals a linear equation, y double dot equals another linear equation, and I don't get into the details of this equation. Believe me, these are the equations of motion of the 3D linear inverted pendulum. And again, you can check that it does have this symmetry map. So it's a 3D leap with all these equations, you can show that it's a symmetric hybrid system. And what does that mean? Why is that important? Because it does have symmetric periodic orbits, as you see. Right? So as you see, these are the symmetric solutions of this 3D linear inverted pendulum. You start from some point, go back, hit the switching surface, which is this circle here, the switching surface. And then based on the impact map, you back to the initial point. So you have this loop and infinitely many of them for different speeds, as you see here. Okay? You might say that was simple because the equations of motion were linear. So 3D linear inverted pendulum is simple. So how about this one? This is just a random symmetric hybrid system that I'm making. So I give you this equation of motion and ask you, find the periodic orbit of this system. How would you do that? You would search for it? It's not easy, right? You see this tangent sign and everything, right? But it turns out that the exact symmetry map that existed for the 3D linear inverted pendulum, we can easily check that it is a a symmetry map here as well. So this becomes a symmetric hybrid system. So automatically, even without even bothering yourself solving the equations, you can say it has the periodic, symmetric periodic solutions, and you can identify easily these solutions by fixed point of the Poincare. How about more complex bipeds? Right? Because at the end, my job is to design a control for a very complex biped. So let's get into more complex bipeds. Recall the symmetry map of this one. This is, by the way, a model of Marlowe, the famous bipedal robot at Michigan that has mastered the wave field in Michigan as well. So this is a simple 2D model of Marlowe. So it does have this symmetry map. So we can verify this X is the X position of the hip, Z is the height of that, and so forth. So this one will have, some symmetric periodic or some symmetric solutions out there. But how about the impact map? Is it also satisfying a symmetric hybrid system conditions? Even if it does, you have some symmetric solutions in a space of 10 degrees. Because it's 5 degrees of freedom. In the state space, that will be 10 degrees of freedom. Even if you have symmetric solutions, who guarantees that these solutions are stable? Actually, that's because I didn't talk about control so far. So far, I talked about this, but we do have control. Of course, you have to use the actuations in the robot, So that can be modeled as a dynamic system like this. You have f of x, and so far I talked about this part, only this part. And I said, is this f is symmetric, and so forth. How about this control? Actually, when the robot is built, indeed, this is given to a control engineer. And then the job of the control engineer is to figure out what u will be. How to design u as a function of time or states, okay? So in order to explain that, and the idea of how to design that u so that we don't destroy the symmetry of the whole system, because that's the goal, right? Because if you don't destroy, what happens? You get symmetric solutions, symmetric periodic orbits, and that's what we want, okay? So I have to make a quick detour and talk about just one slide about virtual constraints, right? So look at this double inverted pendulum here. So a double inverted pendulum, 2 degrees of freedom, and one controller, which is the actuation here. I'm assuming that there is no actuation here. So one actuation here. For some reason, I'm interested to make theta 1 equals to theta 2. I don't know why, but I'm just interested in doing that. And all the time. So which means that theta dot 1 is equal to theta 2, and theta dot 2 is equal to theta dot 2. And theta dot 1 is equal to theta dot 2. So these constraints are enforced by the controller U, or by the actuator U. And that's why they're called virtual constraints. They're not physical, actual constraints. I make U of theta 1, theta 2, such that these two conditions hold true, okay? So these are called virtual constraints. And after these conditions are satisfied, you get a reduced order submanifold of the system, right? Or the reduced order dynamics, where theta dot 1 is equal to theta 2, theta 1 is equal to theta 2, and theta dot 1 is equal to theta dot 2. What's the dimension of this space, by the way? So I had the 4 dimensions here, 1, 2, 3, 4. I have 2 constraints here, so it's 2 dimensions, right? That's why it's called reduced order system, reduced order zero dynamics, or dynamics. So with that, I get to the definition of symmetric zero dynamics, which is how you design U. I'm trying to get into this question, how to design U so that you don't destroy the symmetry. So this is your system with control. As usual, I'm assuming that this f of x is a symmetric vector field, so that's out of question. I don't worry about that part. The second condition is a condition of g of x. I don't get into the details of that, but I'm just telling you that legged robots, they satisfy this condition. So these 2 conditions, I, as a control engineer, cannot touch. This is given to me. But how about the last one? I'm saying that if this zero dynamics manifold, this reduced dynamic submanifold or subspace that I define using my controller, if this is invariant under the symmetry map, then look at this equation. Xz is the restriction of the vector field to submanifold. that is symmetric. In other words, the reduced dynamic, which is now much less in terms of the degrees of freedom or the states, remains symmetric. So it's all about this third condition. If that third condition holds true, then you get this condition, which means that you live now in a lower dimensional space, but still you are symmetric. Okay? So that third condition is what I define as symmetric virtual constraint. So any virtual constraint that can guarantee that condition, the invariance of Z under G, is, I call it symmetric virtual constraint. Another way to define it is that, and again, remember that once you have your virtual constraint, you have your controller defined. So this virtual constraint, I'm saying that they are satisfying this equation. That is, the virtual constraints are invariant under the symmetry map. So then I call them symmetric virtual constraints. So now back to the example that I gave you, the 5 degree of freedom biped, the symmetry map. This one has 5 degree of freedom and 4 actuators, 2 at each leg. So it has, in other words, 1 degree of underactuation. Okay? So you can guess what would be the dimension of the reduced system, right? Because you have 5 degree of freedom, 4 actuators, so 1 degree of underactuation.